My dear, the world is an illusion, right? And the reason I'm saying this is this inequality that we are supposed to prove looks fairly complicated, right? It's product of three different integrals. And how on earth am I even supposed to deal with this, right? But if you just keep yourself calm and try to think and try to see, this is actually pretty easy because you see the limits of integral over here, those are almost they're discrete, right? But still, the integrand in all of them are same. The 2 by pi in all of them are same. So, if in any way, if I'm able to transform this product into a sum, then maybe some good things will happen, right? And how do you do that? Okay, so to do that, there's really uh, popular inequality, AMZM inequality, right? Which says that, let's say if I have three positive numbers A, B, C, then cube root of A, B, C will be less than equals to the average. This is our arithmetic mean, and this is our geometric mean, right? So we're gonna use this, but there's no cube root, so I'm gonna modify this a little bit. So A, B, C will be less than equals to A plus B plus C by 3 whole cube, right? So now if we use this, our expression will simplify a lot, and then after that the solution is almost obvious. Okay, let's see how it works. Uh, yeah. So I'm writing three terms. This is fairly long though. I need to write a lot. Okay. Now, these terms, first of all, I do need to verify that all these quantities are positive, and turns out because the integrand is positive, right? And this is going in a positive direction, so of course the integral will also be positive. And yeah, and also this is multiplied by a positive number, so it's positive. So if ABC are positive, now you can use this inequality. And if I use that, this will be less than equals to sum, right? I can take 2 by 5 common, actually 2 by pi common, and then just sum all of them. 0 to pi sine square x by x square dx plus 2 pi to 3 pi sine square x by x square dx plus 4 pi to 5 pi sine square x by x square dx, right? There's sum divided by 3 whole cube, right? Now, also let's look at this. There's a strict inequality over here, and also it's just 1 by 3 whole cube. So maybe in some ways we have to reduce this expression over here to 1 so that uh, we will have 1 by 3 whole cube, right? And also because there's a strict inequality, uh, maybe, okay, now what you might want to do is, okay, we know that okay, over here, if there was also, let's say, from pi to 2 pi, from 3 pi to 4 pi, we could have added all these integrals, right? So since there's no such terms, and we know that, again, those, let's say, integral from pi to 2 pi of this quantity is positive, right? Because the integrand is positive. So since there's no such quantity, and what you can do is, okay, this will be strictly less than the integral from 2, uh, okay, the integral from 0 to pi, and then from pi to 2 pi, and then from 2 pi to 3 pi, and then from 3 pi to 4 pi, and then from 4 pi to 5 pi of sine square x by x square dx, right? And I'm saying this is strictly less because these quantities will be positive because the integrand is positive and the integral is running in positive direction, right? So yeah, in this cube, right? And now I can now write this as on 2 by pi integral from 0 to 5 pi of sine square x by x square dx, right? Divided by 3 whole cube. Now, there's not really any like easy way to do this integral that we have right now. But again, since we are just dealing with inequality, I can again write this as being less than 2 by pi times integral from 0 to infinity of sine square x by x squared dx, right? Because this one is the real popular integral. And again, notice that since I'm just adding integral from 5 pi to infinity, right? And again, the integrand is positive. Also, the limits is going in positive direction. So this is a positive quantity. So that's why this previous expression is less than this expression, okay? So if it was negative, then we would not have been sure, but it's positive, so we are sure. And now, actually, this one is a really popular integral. It's just like a different form of Dirichlet integral, and you might be able to find this integral everywhere on the internet. I mean, there are lots of videos. There's also videos by black pen, red pen, right? So yeah, let me just use the result for now, and then after we've proved the inequality, I will also give a really easy proof. Like, yeah, I'm just gonna destroy this integral. Yeah, but let's prove it first. So yeah, this expression actually equals to pi over 2. Yeah, seems interesting, no? Because the pi appears here. And not just this, let me also give you something more. This also equals to pi over 2. But this doesn't really continue to third power or fourth power. This, yeah, this first two powers, so it's pi over 2. And now, so this is equals to 2 by pi times pi over 2 by 3 square. So this 2 by pi was a hint that they're going to cancel out. And this is actually not second power, this is third power. And that gives me 1 by 3 cube. And that's why we have proved that this initial expression is strictly less than 1 by 3 cube, which is what was to be proved, right? So now let's try to prove that this integral, and in a really easy way. I mean, we won't really need a lot of efforts. It's just like destroying the integral. Okay. So okay, first of all, let me share something. We're gonna use this really powerful tool called mass identity, which says that if I want to find integral from 0 to infinity of f of x times g of x dx, then this will just be equal to integral from 0 to infinity of Laplace transform of f to the world of s, let's say Laplace inverse transform of g to the world of s ds. So what it basically says is if we have integral from 0 to infinity of a product, we can just take Laplace transform of one of the function and Laplace inverse and then take the integral. This will be helpful for us. Now what I'm going to do is I'm going to take Laplace of sine square x and Laplace inverse of x square, okay? To find the Laplace of sine square x, let me first break this into 1 minus cos 2x by 2, and for x square, 1 by x square, right? Now Laplace of 1 minus cos 2x by 2, this will just be 1 over 2s minus, again 1 over 2, after that s by s square plus 4, right? And for 1 by x square, this is just gamma 2 by x square, so this will be just s and then ds, okay? You can actually verify this from a Laplace transform table, right? I'm just using this. And now after this, I can actually multiply by s to get 1 over 2 minus 1 over 2 s square by s square plus 4, right? ds. Now after that, integral from 0 to infinity, I can take 2 times s square plus 4 common. That gives us s square plus 4 minus s square ds. S square cancels out, and that's really nice. So we have now 2 by s square plus 4 ds, right? And this is equals to 2 times 1 by 2 tan inverse s by 2, right? From 0 to infinity, 2 cancels out, and this is just tan inverse infinity is pi over 2 minus tan inverse 0 is 0, so this gives us pi over 2. And that's how you can easily solve this integral. Like after the first step, after using the mass identity, everything was just algebra, some high school things, Just like mass identity is actually so powerful. You can even prove the other one, like this one. Like in YouTube, people have a lots of long videos proving this, but if you use math identity, it's just one liner. Because if you use transform of sin x, it's just 1 by 1 plus s square. Laplace inverse 1 by x is just 1 ds, and now this is just tan inverse s from 0 to infinity, and it's proved pi by 2 minus 0, which is pi over 2. It's also not hard to prove math identity. You just need to know the definition of the Laplace transform, and you can easily do it. Okay, so yeah, we have proved this integral, and that also completes our proof of the inequality. I hope you enjoyed this, and I hope how simple and elegant this was. Right? I hope you enjoyed the video. And thanks for watching. I look forward to seeing you in the upcoming videos too.